So today we start with the following exercise. So the exercise is that when first assume that we work with a vector space on R, and we want to show that the weak topology is Hausdorff. So so to solve this exercise, we are going to use the definition of a Hausdorff space, and so pick up any x1 and x2 in our Banach space. I called here E, and assume that x1 is different of x2. Now, so we look for two open sets, U1 and U2, in the weak topology. So E is a Banach space, but it's a Banach space for the usual norm. So here we don't look at those open sets for the usual norm, but open sets for the weak topology, as defined as above. And so, such that x1 is in U1, x2 is in U2, and the intersection of U1 and U2 is the empty set. So there was a remark on the chat saying that why don't we look for a hyperplane separating two open sets, separating x1 and x2. So that's a good idea, and that's the geometric idea that we are going to use. But for that, we look to define a good phi, a good function phi in the dual. So because why are we heading to this direction? Because the open sets R of the weak topology are defined thanks to our function phi in the dual set. And so what's the idea here? Since x is different of y, let's define one function phi. I want to define a linear continuous function phi, and I said this. Okay, let's choose phi such that y minus x phi at y minus x is 1. So I want phi to be linear, so I have no choice. So I let think you about that. So I define a linear function on span of y minus x, and to do that, it is sufficient to take phi of y minus x equals 1. What? So in order to construct U1 and U2, we are going to define a function phi, because the open sets of the weak topology are defined thanks to the function phi's. So the simple thing is to start by defining a phi such that phi of x2 minus x1 equals 1. So this, we already done that, but I come back to that. This defines a linear functional on span of z with z equals x2 minus x1. Why? Because then I want phi to be linear, so phi of alpha z equals alpha phi of z equals alpha. And so I define like that my function phi on span of z. And you can check that if I look at phi of z1 plus z2, this will be equal of phi of z1 plus phi of z2, because this can write as phi alpha 1 z plus alpha 2 z, and this is alpha 1 plus alpha 2 phi of z, which is alpha 1 plus alpha 2, which is phi of z1 plus phi of z2, phi of z2. Okay, so this is a linear functional and it's continuous. It's continuous because if I look at for any alpha z, this is equals to alpha, and so this is equals so I want to make appear here alpha z so what I want to show that this is less than alpha z times a constant, right? And this is, so this is equal alpha z divided by z. So at the end of the day, this is 1 divided by z times alpha z. So as a general fact, I have a phi of w is less than norm of w times a constant. So this shows that phi belongs to, not e prime, belongs to, so is a linear. So phi is a linear continuous function on span of z. Okay. All right, so what can I do with that? All right, so now we have a bounded linear function defined on E, and we already know this comes from the Ann-Banach theorem, the first theorem that we saw in the course. Then we can extend it to a bounded linear function defined not only on span of y minus x, but on E. All right. So what's the interesting thing? What's the interesting fact here now is that if I write now, so y and x are on E, so phi of y is defined and phi of x is defined, but phi is linear, so phi of y So y is y minus y plus x. So y is y minus x plus x. So phi of y is phi of y minus x plus phi of x. So phi of y is phi of x plus 1. So those now are distinct. So the question now, how can I get my open sets now for the open topology? So the answer is yes. How? I can now separate as follows. You can write U1, for example, to be all the points in E, all the Z in E, such that phi of Z is less than phi of x plus 1/2. And this contains, of course, phi of x. And this is an open set. This is an open set of the weak topology, because U1 is phi minus 1 of, this is an open set of R. So we're good. And also, U2 is the way around. I define it as that, and it's also an open set. And now, the intersection of U1 and U2 is empty. So we're done. All right. Okay. So any questions with that?
Excusez-moi, monsieur, j'ai une question.
Yes, please go ahead.
Comment vous définissez U1 et U2 de des ouverts?
Donc U1 et U2, ils sont définis là, vous voyez?
Ouais.
So let's go back to English. U1 and U2 are defined as this. So this is, by definition, those are open sets of my weak topology. So because it's defined as phi is a bounded linear function, and so phi minus 1 of an open set of R is an open set of the weak topology. So U1 and U2 are open sets of the weak topology because they write as phi minus 1 of open sets of R. This is an open interval in R. This is an open set. And phi minus 1 of an open set of R is an open set of the weak topology. And so you can check that, of course, these two intervals in R are the intersection of those two intervals in R is empty set. No value of R can be at the same time in this interval here and at the same time in this interval. So the intersection of those two intervals is the empty set. So also phi minus 1 of this interval and phi minus 1 of this interval, their intersection are an empty set. So next we are trying to solve the same exercise, but instead of R, we're working with a vector space on C, the complex numbers. So show that the weak topology sigma E prime is Hausdorff. So now in this exercise 20, this is the same, but with C, the complex numbers. So we are going to try to copy the same proof as in exercise 19. So let's try to do that. So we look for, so first we have two points in E, X and Y. X is different of Y, and we look for two open sets UV. Oh, I changed the name. I call it UV now. In the weak topology such that X is in U, Y is in V. And we want that U and V have nothing in common. So the intersection of the two are the empty sets. So let's try to define our function phi as before. And let's try to set phi of y minus x equals 1. All right, so as before, this defines a linear functional on span of y minus x. So by the complex Anbana theorem, I can extend it to E. Okay, but now if I look at the distance between phi of x and phi of y in the plane, in the complex number plane, this is 1. So phi of x and phi of y are at a distance 1 from each other. So next it's the same. I will define u. So now the ball of radius 1/2 centered at phi of x, and the ball centered at phi of y of radius 1/2. Those are the intersection of those two balls are the empty set, right? You can draw a nice picture of that, and then I can just define u and v as phi minus 1 of the first ball centered at phi of x, and v as phi minus 1 of the ball centered at phi of y. And by construction u and v, the intersection of u and v is the empty set. U contains x, v contains y, so we're done. So next, so you have the notion of neighborhood. So when you have a topological space, we say that V is a neighborhood of X if there exists an open set U such that X is in U and U is included in V. This is a classical definition of a neighborhood for a point in a topological space. Next, you have also the definition of a basis of neighborhoods of X. So we say that B is a basis of neighborhoods of X if for any neighborhood V of X, we can find a U in B, there's a typo here, such that U included in V. All right. So with this definition in mind, I propose to you the following exercise. Okay, so you can first start in R and then go to C, or try to do it with C directly. Okay, I'll let you with that.
Excusez-moi, monsieur, on ne vous entend pas.
Yeah, so sorry, my micro was off. So let's. So the point is to prove of the exercise 21, exercise 21 is to prove that the sets that write as this are a basis of neighborhoods of X for the weak topology. So a few words about the correction of that. So you choose a X in E, and let's assume that V is a neighborhood of X. So by definition of a neighborhood, this is a classical definition of neighborhoods. It's in any topology. V contains an open set which contains X. Okay? Now, by the definition of the weak topology, this open set contains the intersections of a finite so the intersection of reciprocal images of open sets Oj and phi I, those are linear continuous applications. Okay. Okay, so the point is to I remind that the open sets of the weak topology write as union of finite intersections of phi I Oj, where phi I is a linear continuous application and Oj is an open set in K. All right. Okay. So those indexes, we can write it a little bit different, but the point is that this is finite. I have only a finite number of applications and open sets. Okay, which means that phi I of X belongs to Oj. Okay, but Oj is an open set in K, so it contains a ball centered at X. So you can write it as so you have that. All right, but now since I work with finite sets, you can take epsilon as the minimum of all these epsilons ij. So therefore, you have that X belongs to the intersection of the ball centered at phi ix and epsilon. So there's no more J because I took the minimum here. And that's exactly the same that this. Considering that I is a finite, so I write it I, but you can write it 0 when till n. Okay. So this ends the session of today, and yeah, see you soon.